Hello, everybody. Thanks for coming to my talk. And let's cut to the chase. So how many of you are actually not a Haskell developer? Not Haskell developer. OK, thanks. Me too. But I love this language, because every time I use it, I learn a new functional programming trick. And this is the cornerstone of this whole talk. So basically, whenever you use Haskell in your personal project, or a company tool project, or a team tool project, you can become a better functional programming, no matter what language you use in your everyday job. And this is a story of such a project. We'll do a full-blown application, front-end and then back-end. There will be lots of slides, types, and functions, so brace yourselves. I know the time isn't very good, but hopefully it will be OK. So during this presentation, whenever you ask yourself, why bother, why this guy is doing that, or something like that, it doesn't make any sense, remember this slide. That's why I'm doing it. So we need to have everything explicitly said in the code. Configuration, side effects, any external dependencies, everything needs to be there in the code so that we can reason about that. It's more readable that way. And 6 months from now, whoever is using our code, maintaining it, be it us, he or she knows exactly what we are doing. And of course, the solution is to use pure functions and types. OK, now the domain. We are using GitLab for storing the code and version the code. Also, we are using it to do a code review process. So GitLab is a GitHub alternative that you can host on your own. And MergeRequests application, MergeRequests application we wanted to create this during this talk is a wrapper around this GitLab service. So we want to have more information about the whole code review process. For example, we wanted to see the correlation between the size of the change that needs to be changed, it needs to be merged, and the time it can take, so the developer can know exactly what to expect based on the 1,000 merge requests we've already seen in our code. So this application on the right, this is what we are going to implement. OK, and this is the application architecture. It's not very complicated, and there's a GitLab server at the bottom, which we'll use, and the backend part will just get the merge request from the server, calculate some stats out of that, and then pipe it to the front end. And we'll use Elm and Haskell to implement that. Backend part is in Haskell, and Elm will be used in order to do a web application. Okay, and yeah, I owe you an explanation. Elm and Haskell share very similar syntax, and you are all not Haskell developers. That's why I have one slide tutorial for you. And so one slide, I hope it can be seen. Right? Do you see it? OK. So this double column here is a declaration of the function. So we declare a function which is called sum3int, which sums 3 ints. So as you see, in Haskell, we say that it takes 3 inputs, and the last type is always the output type. And there is one line here. In Haskell, we don't have any bodies, function bodies, so it's just always expression. So we define functions using expression. And this is the definition using one expression. So sum3ints ABC is defined as A plus B plus C. And the rest of this module is just function applications. So sum3ints of 1 and 2 returns a function. Here is a function. So it's a partially applied function, just 1 and 2. The second one is 1, 2, 3. So we return 6, of course, because it's a sum of those 3 numbers. And then, as you see, the application is the strongest operator, the strongest bounded operator. And there is a compiler error in the third example. Some 3 ints of 1, 2, and a function is, of course, not something we would type check. And to get rid of this compiler error, we can use brackets, of course. And this is the most scariest part for every newcoming Haskell developer. What is this $sign? So the $sign is equivalent to those brackets. So we can, instead of having 2 characters, we just place a bracket and Yeah, it's easier that way, but it's totally equivalent. And more complicated stuff, we define a factorial function here, and as you see, there are just two expressions that define this function with pattern match on 0 and n, and that's why that's how it works. And here, the dot here is a function composition, so we compose factorial n length functions in order to get a new function here. And of course, we are using, again, the infix application operator, this $sign, in order to apply it. So it returns 6 because the length of the list is 3, and we pass it to the factorial function, and it returns 6. And the last example is head of a list of any element, A, and that returns maybe. So for you Scala developers, there's an option type. This is a maybe type. This is very equivalent. For a none case, we have a nothing, and for a some case, we have just. So yeah, we pattern match on the list that we get, and if it's empty, we return nothing. If it's not, then we return the first element. All right? So basically, now you know some Haskell. So we can move on to implementing our first module of the application. So this is a HTTP client. We'll use servant, Haskell Servant library. This is a set of libraries basically for HTTP programming, but it takes over all the HTTP stuff from our hands, and we can focus only on the APIs that we want to implement or consume. So all those APIs are just types. This is architecture again. And we use this fetcher in order to fetch the merge request and then loop over it, then store in the memory inside our RAM. And that way, we'll have always the fresh batch of merge requests running in our memory. And this other part can just use what we have stored here and go to the front end and without any blocking. So let's go through the Gitlab API very quickly. You don't probably see it, but it just says that whenever you do a get HTTP request for projects, project ID, and then /MergeRequests, it returns some kind of JSON, and this is a simple JSON file, a simple JSON response. So it's an array, and there are some identifiers, state, title, upvotes, downloads, author, and whatsoever. Okay. So data merge request. There's an ID, IID, title, and things like that. So this is just a Haskell data structure that we defined in order to fetch them. And those are just two type class instances. Merge request is serializable from and to JSON. So that the whole code is enough in order to do a serialization and fetching from the server. Okay, so it's data here in blue font. Then merge request in the red font and the equal sign. And then you can see no, you can't. But you may imagine that there is a blue kind of font which also says merge request. This is a constructor of our type. And then in a grayish font, unfortunately, there is an ID, IID, title, state. So everything we've seen here, basically the same stuff that you've seen here can be found in this data structure. And here you have instance in yellow and from JSON merge request, which is red, and to JSON merge request, which is also red. So we just defined that your data structure merge request is serializable and deserializable from JSON. And let's talk for a bit while waiting for the lights to be turned off. Let's talk about doing the smiley stuff. Oh yeah. Where was that? Is it okay? I know. Yeah, now we're talking. Okay, it's better, right? Okay, good. So, how to do a smiley face then? So you need to do a colon and an angle bracket, right? Have you done that? Whenever you do the Facebook Messenger or iMessage or anything like that. Who does that? Evil smiley face. No, you're using the normal one. So we also can do that in order to define our API type. So this is the same smiley icon you use in your messaging. So this is one type. I will repeat this quite often. This is just one type. So as you see, it corresponds to the path you all can see here. First we have API, then we have v3. So the smiley emoticon icon operator is just something that we replace slash with. And here are the red ones are the most important that we need to focus on. So header is a private token we need to provide in order to our request not to be in order to do for the request to be authorized on the GitLab server. So it's a string, then a slash projects, then we have a project ID which is captured here. So we know it's an int, then slash MergeRequests slash query param page, which is a string because it's a I will talk about that. And the return type is JSON type. JSON type, and here we have a paged list, the brackets list of MergeRequests. Paged list of MergeRequests mean that in the response, GitLab sends us the URL for the next page. And that's why we have, that's why the page is in strings, because it can be hash or anything like that. So page just captures the URL, and we can fetch the next page automatically. Okay, so in order to query the GitLab, we need to provide a function. So we will use the API query function in order to get all those merge requests from the server. And the first parameter that we provide to this function is a URL to query. Then we do things that correspond to the API type we just defined. So the first one is a maybe string, which is a token. The second one is a project ID. Then we have a page, which is a string, also maybe type, and the whole very big complicated return type, which is the most complicated you will see during this presentation, and we'll dive into it in a minute. So it also corresponds to the type that we defined, to part of the type that we defined as our API. So either T, servant error, IO page, merge request list. So yeah, it's a long type, return type. And whenever you see something like that, you can imagine that this is a structured type. So it's either T, which is parameterized with two types. The left one is servant error. The right one is IO of paged merge requests. I said, you know what is the list of merge requests. The paged one I just described is just a captured response that we can get a URL for the next page to. And IO is the one I want to talk about briefly now. So Haskellers say anything is in the IO, then Haskellers say that it's an action. It's a side effect. So whenever we want to fetch something from the server, we need to go there and retrieve the list. And this is side effect, right? It's impure stuff. So whenever we do something like that, in our case, it's just fetching from the server, we just wrap it in IO. And we can't do any side effect in Haskell without wrapping this in IO. So this means that whenever we see IO in the type, we know that it's an impure stuff, side effecting stuff that we got from the real world or the external world, so to say. For example, the merge request list, which we fetched from the server, and we can't get rid of it. Can't. So we got this IO impure stuff. We can do calculations in our functions with it, and whatever we return needs also to be wrapped in an IO type. So we can't get rid of it. If we don't do that, we just get a compiler error. So just remember, if you want to say to the IO, leave me alone, then it will say nope. Remember. And this is very important. That's why I have a second slide for that and a quiz for you. What's the difference between function 1 and function 2? Who knows? Return time, but what does it mean? Yeah, the second one has side effects. So function 1, we know that the merge request list is strictly defined as an argument of string. So we can only, so whenever we put the same string as an argument, we always get the same list of merge requests. The same cannot be said about the second function. So, for example, in Haskell, whenever you want to do a hello world program or something like that, you need to work with IO type, which is very hard, right? But put string ln is a string function that returns IO of unit, for example. So yeah, it shouldn't be so scary anymore for you. So that's either T type is the only one left that we need to define, to explain from our return type. Either T is something very similar to either. It can be left or right. If it's left, then it contains servant error, which is just a server error, disconnection or a timeout or something like that. And if it's successful, then it returns right with the IO type and paged merge requests. Okay? So so far we've just talked about the type of the function that we want to use in order to fetch the merge request from the GitLab server, and now we just need to implement this. And this is one expression implementation. Servant gives us the whole generation based on our API type. Okay? So this is all, and we can now just API query this, and we'll get a list of merge requests from the server. But it's not very nice because it takes 4 elements. So let's define another function which we'll call paged merge requests, and it will just get 2 parameters as input. One of them will be a app config. Now you probably can either see it because it's grayish stuff. So it's token, server host, server port, the static things that we have inside our application. So it's global throughout the application. We just pass it around, and everybody knows what to do with that. And that's why we get a function which takes 2 parameters, but the same return type as you see. So let's go to the implementation. It's slightly more complicated than the previous one, but it's also one-liner, right? It's just a function application. We just wrap stuff around. For example, we create a URL and the token, which is maybe, and project ID, things like that. Remember that maybe it can be nothing or just a. And the last function of this module, the one that is public, we just get all merge requests from just calling this one function. And it will also reuse the paged, the last one we defined, so this paged one. And as you see, there is a difference in the return type. The paged one is gone. So all merge requests mean that we get all the merge requests from the server, not just one page. So remember this return type here, what paged merge request returns, because it's better for you to understand this one. And if you get bored with all the slides with the code, the next one is with the image. So it should be easier for you to comprehend this one, and it's the most complicated we've seen so far. It uses a recursion, and the recursive function, which is internal, is a fetch page function. It takes 2 parameters. Current, which is the current set of results we have, and it's empty list in the beginning, and the current page we want to fetch, which is 1 in the beginning also. And remember the type, paged merge request. What type is it? It's either T, servant error, IO, paged merge requests. So paged response is a different type. So this left arrow and the do notation unwraps the things from the either T, IO, servant error, IO, and it's a type paged merge request. So we do this kind of stuff and get the MRs, concatenate them with the current list, get the new page, and then pattern match on the page. And when there is a new page, we just continue recursive calls. And when there is not, then we just finish with the recursive calls and do a return all MRs. Return is another function, and it returns those all MRs in the context the whole do notation is in, which in this case is either T servant or IO. So this works pretty exactly the same like in for comprehensions in Scala. And yeah, so if you got bored with the last slide, then you just need to remember that you can do side effects without the I/O. But for example, it can be raising temperature of the CPU or computer, right? It's a side effect that you can do without I/O. Okay, so this is the whole module. All the things that I've talked about just now, those are the functions. API query, which is generated by servant, paged merge request, which just uses API query, and all merge request that just uses the paged merge request function. And this is the type of our API. Again, this is just one type. Whenever we change something in the type, the compiler won't allow us to do anymore. So whenever there is a change in the API itself, for example, GitLab changes the API, we just change this type and then fix the compiler errors. And it should work. Yeah. So the same story with comments, very similar situation. We just need to fetch from another path and serialize to different type here, merge request comments type, but it's also a list. We'll use it later. And now onto our business logic. Business logic, which just takes the things that we fetched from the GitLab server and transforms them into a list of the stats of each of the merge requests. And there is a stats, of course, there is a stats object also, and this just can be serialized to JSON. We don't need it to be deserialized from JSON for now. So we just say that it's instance of to JSON. And those two things will be calculated just for the sake of this presentation. First of them is time to merge. The second one is comments quantity. And calculate stats function, which is our business function. First things first. So what's missing here? What type is missing here? IO. Yeah. So no IO. We just our business function doesn't have to take anything IO related. It's testable this way, right? So it's a good thing that we don't have any IO here. And yeah, what it does, it just calculates time to merge for us and returns a merge request stats object. Nothing more. So to connect all the dots, we need to have one function that takes the merge request from the server, calculates the statistics out of them, and then save into our in-memory storage so that the backend service can reuse them. And this is what the function does. And it creates a config. Again, say hello to our do notation here, but this time it works in a different context, either T of string IO. And yeah, we take the app config, then we fetch all the merge requests, then we fetch comments, then we define the fetch comments function. We map all those comments into fetched comments, and then zip each merge request with the list of comments, calculate statistics out of it, and write to storage. Question?
Yes.
Yep.
What happens if I have got error during the web, this web layer? I don't see IO on the error side of either. So
Okay, yeah, very good question. So what happens whenever we get an error, which we got rid of? Because all merge requests and all comments receive a servant error, right? No. So it's either T, it has IO inside it. So everything, as I said before on the several slides before, when you see it, so it's also, yeah, either T has IO inside it.
But not on left side, on servant error, there's no IO.
Yeah, I wanted to ask a similar question.
Yep.
I call either T,
yep.
Should be inside of IO.
Yeah, and this is the case. So this structure, either T, is not either, The T means just that what you were guys all saying, okay? So in fact, it's IO as a top layer, but it's hidden inside, okay?
Why is there another IO inside?
Just for you to have a better programming experience, so that you don't have pattern match at different levels, okay? So it's just an easier way to program. Okay, and we at the end, we just write to the storage, as I said. So this function, again, fetches the merge request, calculates the stats, and saves them into the in-memory storage. And app config is either the string IO of app config, because it's environmental variables, and error to string is something you guys asked. So we just replace either servant error with either string. And now we go to the server side stuff, and as you see, the API type is also something that defines our server side, not only the consumed client side. And so we have two endpoints, MRs and front stuff, which is raw, and MRs receive on each get. We just return the list of merge request stats, and there is a definition of this API path. We just read from storage whenever we get MRs, and serve directory with our front page using the serve directory function. And the main function, which is the last stuff you will see from the backend side. So main function creates a new storage in memory, then asynchronously fetches all the MRs and saves them into memory, and then at the end we just run in the main thread. We just run our server on 8080. Okay, And we did it. This is all functions we've done and the API stuff we've done. So all merge requests fetches from the server, the same story for comments, then calculate stats, our business logic function, and the fetch MRs and save stats function just connects the dots, and the server function just returns the server. Nothing more. So that's all those three blocks are implemented. And just a quick side note. So we have just one type as our API. So our API is defined in one type. We can, of course, implement the client for it. We can implement the server, as you've seen. But also we can, for example, auto-generate JavaScript client for the API. So again, API is just one place when we change something, and all the changes that are needed in our code just spread across all the other layers of our application. The same for documentation. So those two things can be just auto-generated based on the API type. And this can be more descriptive than what I've shown you here. So the documentation and JavaScript clients are really nice looking. And let's do the front end. So we'll use Elm for that. And Elm is a very, okay, I like Elm a lot because it has all the three things I love about programming. This is streams, types, and of course, one more thing, which I don't remember. No, it's virtual DOM. Yeah, I just remembered. So it's virtual DOM. And all those three things, I will explain a bit. So the requirement for this application is just merge request stats in a table. And each 5 seconds, we just refresh all the list, and that's all. So dynamic table of our stats we calculated on the server side. So Elm architecture is model, view, update. And update and view are functions. So model can be anything we wanted it to be. And the update function takes model and action as input parameters. And what update function does, it returns a tuple of new model, which then become a model, in fact, and effects. And effects are data. For example, an effect can be, please get me something from the HTTP endpoint. This is kind of effect. And then this effect can be replaced in Elm runtime, replaced with the action. And action can be, for example, here's the result of the HTTP thing you wanted. Okay? The model also can be piped into view function, which then translates it into HTML object. And this is what I've briefly spoke about. Just this is a virtual DOM object. So Elm rendering just gets this HTML object and checks what's currently displayed in the browser and diffs it with what we want to display now, and just does the minimal list of DOM operations in order to achieve this result. So it's more performant this way. Virtual DOM does that. So whenever you use React.js, for example, it's the same story. And so any questions about the Elm architecture? Okay. So the puzzles that we need to solve here are just three pieces, the one model and 2 functions. And the model looks kind of similar to what we've seen so far. And this is Elm code. So there's one obvious difference, which you'll notice in a bit. But the merge request is the same. The merge request stats is the same as on the backend side. And the model here, there may be one surprise for you. This is a list of merge requests. OK. But also, it's a last refresh time there. So in Elm, we cannot take the current time. So we cannot ask Elm, hey, tell me what's the current time, because it's not pure, right? Every time we call it, we just get another function. So the constraints on Elm doesn't want us to do that. So we need to be more pure and put a last refresh time in our model. And this is actions that go into update action. So we explicitly define what kind of actions can be done inside our application. And it cannot be more than that. So in our application, we can update the list with the new list, or we can tick the time with the current time. And the action are just defined, update list or tick, are of course piped into the update function alongside with the model, and we pattern match on it. So update list, we just return a new model, where MR stats is a new list, and a tick effect. And that whenever we pattern match on tick with a new clock time, we just check whether the last time we refreshed is 5 seconds ahead or something like that. And then if it's not, we return the current model with the new tick. And if the 5 seconds passed, then we return the new model with last refresh time and the clock time. And the MergeRequest fetch effect function, which I'll show you in a minute, is just the effect we want to do whenever we want to do a refresh. And as you may have guessed, the MergeRequest fetch effect. This is 1 colon instead of double colon in Haskell. So we do a HTTP GET request to our server. This is a JSON decoder which I won't show, but then we pipe. So this is like a pipe stuff. So this result is then piped into maybe, then it's transformed. Whenever it's nothing, it's just done, and when it's just, we just do mapping to the update list we got from the server, and we create the action out of that. So view function, this is the scariest part probably. So each HTML element has a function. For example, div has a function, table has a function, th has a function, and each of those functions take just 2 lists. The first is the list of the attributes inside the HTML tag, and the second list is the list of children of another HTML object. So in this case, we can see that div has this layout, and h1 and table children. And table has this kind of style, t-head and t-body. So each MergeRequest stat in the model is mapped through the stats view, which creates the tr HTML object out of it, based on the things that are in the model. So again, the same architecture, but now with the domain-specific things, we get the model, which is emers, MergeRequests, and the refresh time. We pipe it into update function alongside with tick or update list action. So those are just 2 actions that we defined. No other action can go into our update function. And we produce the new model and some effects. So effects are, in fact, the data. And all the impurity is gone. It's done inside an elm runtime. So elm runtime just calls our update function whenever it sees fit. So the very similar story with view. Each time the model changes, the view function is called, and we just return a new view object. If it's the same, then nothing happens on the browser side. If it's different, then the minimal list of operations is done on the DOM side in order to render it. So fame and glory, this is our application, and as you see, the calls are done each 5 seconds. This is like set of stats we did. So this time to merge, for example, 3 days, 5 days for this merge request, 7 hours, 93 minutes, things like that. So, and one side note, whenever you use Elm, you can do something like time traveling. Okay, you just write your application, you then just run it, and you can pause it, and debug like 50 updates to the left or in the past, and see what was the model, what was the state, and how to debug how this bug came to life. And you can, of course, see it for yourself. You don't have to install anything. You can edit the code and play with Mario. This is like 70 lines of code or something like that, just the Mario stuff. Okay? Please do. So all the links, the backend project, the frontend projects, few movies to watch, of course. And yeah, this is my blog. This is my Twitter handle. And thank you very much.